What is up, good people? We are on section 1.7, day 2, transformation of functions. We're going to be working with cubic functions and square root functions, and we are closing out this chapter. Yes, I'm very excited to do that, and we are and look for a chapter 1 project on the horizon. Very excited. It's going to be awesome. All right, check this out. I've got a new function here. The rule is take the input and multiply it by itself 3 times. Whew, not just 2 times, 3 times. Let's see what happens. Maybe the positive numbers will be easier. So you start with, say, positive 2. Multiply it by itself 3 times. 2 to the third power, that is 8. 1 times itself 3 times is 1. 0 times itself 3 times is 0. Negative 1 times itself 3 times. That's negative 1 times negative 1 times negative 1. Well, 2 of the negatives will cancel out, but you're still left with 1 of them. So at the end of the day, the output's going to be a negative number. Negative 2 times negative 2 is positive 4, and then times negative 2 again is negative 8. So what you see here is you get these outputs right here, and each row corresponds to a point on the graph. And it looks like this. Funky. It's like this S-shaped curve. Not even S. It's what we'll call it a cubic curve, because the 3. This is a x cubed. Interesting. We'll talk about the features of this graph in a second. Here's the square root of x, and if we haven't taken the square root of stuff in a while, when you take the square root of a number, you ask yourself basically what number times itself would give you the number that you see in the square root. So that's the rule for this function. We take the input and take its square root. So if I'm going to choose these x values, these inputs, a bit judiciously here, I'm going to be choosy and not just choose any 0, 1, 2. I'm going to go 0, 1, 4, 9 because I know I have the foresight to know that those will be easy calculations. What number times itself is 9? Maybe you can figure this out in a bit. Let's start with 0. What number times itself is 0? That'd be 0. What number times itself is 1? It's 1. What number times itself is 4? That'd be 2. So when you take the square root of 4, that's 2. What number times itself is 9? You can figure that out. Now, what number times itself is negative 1? You might be tempted to say that it's negative 1, but negative 1 times itself is not negative 1. It's positive 1. Or what number times itself is negative 4? Well, you might be tempted to say negative 2, but it's not, because negative 2 times itself is positive 4. So there's really no number that we know of yet that can, when you multiply by itself, you get negative 4 or negative 1. So therefore, what we've got, you can say this is undefined. You can write this in the table, but really what we've got to do is strike these x values from the table. We have to remove them. They're not in the domain. They don't have a corresponding number that they pair with. So we have to say that numbers like negative 1 and negative 4 and negative 9 and negative 16 and negative 10 and negative 2 and negative 3, all these negative numbers don't have corresponding outputs, so therefore they are not in the domain. They shouldn't be on the table. They don't produce an output. They don't produce any points on the graph over here. Like the entire negative half of the x-axis is just blank. You start at 0 and you can take square roots of any positive number you want. Positive 9 is easy, that's 3. Positive 4 is easy, that's 2. Positive 1 is easy, that's 1. And you connect the dots and you get this kind of sideways parabola. The parabola is definitely sideways like this. Like if you look at it on side, if you turn your notes to the side, you get an exact perfect shape of a parabola. It's just been, it's sideways. So we're going to call this a square root curve right here, and that's another parent function. I mean, this is the good news about introducing these new kinds of functions is that now you can also take transformations of them too. You could do x squared, x to the third power plus 1. That'd be a vertical shift of 1. Or a square root of x minus 1, all inside the function. So that's just more things that you can do, more power you have. Here's another function. if the input is -4, the output is 0. If the input is 0, the output is 4. If the input is 2, the output is -4, and if the input is 3, the output is 0, and all these points in between also correspond to input and output pairings. And beyond that, we don't really have any definition. This is just a weird piecewise function, and it's defined graphically like this. There's not even a table. You could make a table, but I'm going to say at the start that we're defining this graph like this. So let's just check out some of the functions that we could have. Let's check out let's talk about these functions. The cubic curve right here, the domain, all real numbers, because on the table you could take any number you want and produce a y value. And the x value will produce a y value. The range is all real numbers, because all of these on the table, all y values are represented. You can get any number you want on any real number you want over here along as an output. Similarly, if you collect all the x values of this curve, because remember it continues on, it just doesn't stop here, all the x values of all the points on this curve, and you get all real numbers. Every number along the x-axis is represented. And it's the same as the y-axis. Collect all the y values, and every number along the y-axis is represented. So all real numbers for both. Is it continuous? Yes. With one fell swoop of your pencil, you can draw the entire thing without having to jump or break. Does it pass is it 1-to-1? Does it pass the horizontal line test? And the answer is actually yes, because there's no repeats in the outputs. Every output, like the output of 8, has exactly one input. And if you try and find that correspondingly over here, a horizontal line at a height of 8 will only cross the graph once, and that's true for every horizontal line. It only crosses it once. Even right here in the middle, at the x-axis, it only intersects the x-axis once at 0. Are there any extrema? No. No extrema. There is no relative minimums or relative maximums. No maximums, no minimums. What kind of end behavior does it have? It has down, up end behavior. So you can see as x goes to -infinity on the table, y goes to -infinity as well. As x goes to positive infinity, y goes to positive infinity as well. Let's talk about the features of the square root curve. The domain, as we've already said, we've had to strike all negative numbers from the domain because they don't produce any outputs. They can't. So the domain starts at 0 and goes to positive infinity, as we can see here. Those are and graphically, you collect all the x values of all these points. They would, on the graph, they would only represent the numbers 0 to infinity, including 0. What's the range? Same thing. We only have positive numbers in this range. We only have positive y values for these points. Positive and also 0. So the range is from 0, including 0, up to positive infinity. Continuous? Yes. Pass the 1-to-1 test? Yes, for the same reason this one does. Pass the horizontal line test, and yes, it is 1-to-1. Where's the vertex? It is, for both of these, it is 0, 0. You can say that there's a vertex here, and we can say it has a vertex here. What are the extrema? Well, it does have a minimum value of 0. That's the lowest y value on the table. It's the lowest point. The y value of the lowest point on the graph is 0. And where is it? It's when x is equal to 0. End behavior, you can say as x approaches infinity, y approaches infinity as well. This does not have down-up end behavior. It only has 1 up, because x doesn't go to -infinity. You can only say that as x goes to positive infinity on the table, y will also go to positive infinity, and the same thing on the graph. Let's talk about the features of this piecewise function. What is the domain? We collect all the x values on this graph, and it's just the numbers from -4 to 3. And remember, this is an interval here. This is not a location on the graph. I'm not trying to say the x value is -4 and the y value is 3. I'm trying to say that this is an interval of x values. X can go as low as -4 and up as high as 3, and that's it. What are the y values? What's the collection of all the y values? Well, the range would be from -4 to +4 here. Is it continuous? Yes. Is it one-to-one? No, because a horizontal line would cut multiple times. What's the vertex? No, there's no vertex. It's not really applicable. It has some really interesting extrema. It has a maximum value of 4. That's the highest value. If you were going to make a table, the highest value would be 4, and the highest point is right here. And where is that exactly? It's at x equals 0. I'm going to zoom out a little bit, because this is getting to be a bit much. Alright. The extrema, yeah. It has a minimum of -4 here. The minimum value on the table is here. The lowest point on the graph is here. And where is that? When x is equal to 2. It has a relative maximum of 3 here. Sorry, a relative maximum of 0 here, and that's when x is equal to 3. And a relative minimum of 0 when x is equal to -4. Yeah, I think you could probably technically call this point over here a relative minimum and a relative max. Sorry, a relative minimum here as well as a minimum, depending on based on our definition of what a relative minimum is. What's the end behavior of this? That doesn't apply because x doesn't go to positive or negative infinity. All right, let's write a function for each transformation. So here, it's kind of like going backwards from what we've done before. We've seen, we have seen equation table graph, and what we're given the equation, and then we have to say what kind of transformation it is. But here, I'm going to give you the graph, and so if the original here is dotted, this dotted black line, then the blue is going to be a horizontal shift of +2. And so the function, we know it's a parabola, that's the shape, so g of x, the transform function, would be x minus 2 squared. It's -2 because we know I'm taking the opposite of +2, and it's squared because I know it's a parabola shape. Both of them are parabola shape. Here, looking at this vertex, it's actually easiest to see that as a shift of 2 because you're looking at the vertex. I should have said that earlier. Vertex starts at 0, 0, and then goes shifted -1 and in a horizontal direction, and a vertical shift of -1 as well. So this, if we know it's a horizontal shift of -1, then we change it on the inside. We change -1 to be +1 because it's we're talking about the inside portion of this function rule here. The equation is going to be x squared plus 1 squared minus 1. +1 on the inside, -1 on the outside. And if we wanted to, we could like ignore this graph and then take this equation and go equation table graph, and if we plotted out all the points, we'd get this exact curve. All right, so here's the fun one. We've got this blue, the dotted black line is the original. Oh, these points are off. Yeah. Okay. So here's a square root curve. I recognize it as a square root curve because I saw it before in the notes, and I have them memorized at this point. I've been using them so much. Square root curve. It's sideways. It only has one arm, and it has a vertex at 0, 0. Compare that with the transformed blue function, and all of a sudden, this blue version, the vertex is the same, and then you look at the vertex to see if there's any horizontal or vertical shifts. Those shifts are going to be indicated by the vertex. We can see they share the same vertex, so there's no horizontal or vertical shifting, but something strange is going on. It's way taller, it's higher up, it's further away from the x-axis. It has been stretched, perhaps even a vertical stretch. You could say, I identified these points as going through like easy to read locations on the graph. This 4, 2. Oh, I take the square root of 4, you get 2. But look at this. It's been transformed. It's much higher. How many times higher is 6 than 2? Like 2 times what gives you 6? It's 3. So that's how I can say it's a vertical dilation of 3. Everything has been stretched vertically 3 times as high. So therefore, you could say this is, if the vertical dilation is 3, then 3, it should be multiplication on the outside, using our handy-dandy quick summary. So therefore, g of x is going to equal 3 square root of x, 3 times the square root of x. Remember, in your previous notes, we had, if it's a vertical dilation, that means outside multiplication. Here, remember the dotted black is the original. Oh, that's a cube curve. And, oh, interesting. I've identified this point and this point as easy to read places, and it looks like this has been dilated. It's been flipped. So if x here on the dotted original, if x is equal to 1, then 1 times itself 3 times is also 1. But here it's been shifted. It has not been shifted at all. Actually, it's been. You can see the vertex is still at 0, 0. The up arm and the down arm kind of meet together still at 0, 0. So I'm thinking we're looking at a dilation here, and you can go the x value used to be 1 and now it's -2. So what if we divided this x value by -2? We would get +1. Yeah. So the horizontal dilation is going to be of -2. And remembering from the formula, if we want a horizontal dilation of -2, we'd have to have it here. I'm thinking that this might be good to do a table on. And I'm wondering if I can change this. I don't really wanted to say f of all that. I wanted to say, because I've identified it as a cubic curve. Cubic curve. That might be a bit more specific. Yeah. This cubic curve has a horizontal dilation of -2 because x divided by -2. Alright. Let's go down here. Check this out. Here's our funky piecewise function from before. The original is in black. And it looks like it's the same shape. It hasn't been stretched. It hasn't been compressed. It hasn't been flipped. So therefore, we'll call that so therefore, it hasn't been dilated. But all the points have been shifted. It looks like they're 2 units to the left of what they used to be to get the blue. Like you start with black and then you get blue by shifting every point over 2 units. That sounds like a horizontal shift of -2. And so therefore, we'd have to write the function as x plus 2 on the inside. Whatever function this is, the plus 2 is on the inside, and that's what we can write it as. Same thing over here. It's the same shape. It has not been dilated. However, we can read this and see, oh, wait a minute, it looks like it's 2 units higher than it used to be. So that, just remembering our quick summary, we've got that means if we have a vertical shift of +2, that means it's going to have to be outside addition. Outside addition is here. G of x, the transformed blue version, would be f of x plus 2. And that's all we got for today with the notes. Glad to see you're following along. I wanted to say for your audio check, what club? One more club that I was in a lot of clubs in high school, but one that I was in was the engineering club, and I wish we had robotics as awesome as this school. If you're in robotics, you got to know that it's something really super special, and take advantage of that. Because my engineering club was just paper and pencil taking tests. It was I enjoyed it because the friends I had in there were lots of fun, and the teacher was fun too. And while it was open, these tests were group tests. We would submit one test. We'd go to the school, go to the competition location. They'd hand us a couple copies of the test, but we'd have to hand one back as the answers from the group. And gosh, it would have been so much more fun to actually build a robot. So if you're in robotics, enjoy it. I was in engineering club, and that's your audio check. Hey everybody. So we're going to do another Desmos demonstration. I want you to follow along and do kind of the same thing, or at least mirror and play along with me. And you can bring what you create to class tomorrow. So I'm at desmoscalculator.com, and then you can press login, sign in with your Google credentials, and I like to go to the settings and make a big screen so you can see things a bit better. And so what we're going to do is we're going to do a function here. F of x is equal to, and then I'm just going to type in Sqrt. That's a shortcut for square root. X minus h, and add a slider. And then click outside of the square root, and then plus k, and add another slider. So you can see here, I can slide up and down, left and right, the square root. Let's see. Well, the next thing I want to do is change this from square root, delete this, to CBRT, cube root, x minus h. Let me delete all this. And there it is. There's the cube root function. I'm not exactly going to explain the cube root function. Maybe I will later, or maybe you have some experience with it. But the point is, we can make a function and we can translate it as much as we want. Oh, I'm going to put an a out in front also. A, add a slider, a. So this is outside multiplication, so you know it's going to be a vertical dilation. Look what happens when it's negative. Look what happens when it's positive. Isn't that fun? All right, let's do a whole completely new one. Let's do sine, S-I-N, parentheses, x minus h plus k, using the same sliders as before. Oh, and then the a out front, a. So it's a very curvy, wiggly function, and I'm not going to explain it very much. It looks pretty cool, but what you can do is you can use the sliders to shift it up, down, left, right. We could even do, you can highlight all of this and press the divide symbol and maybe type a B here for another slider. This is going to be a horizontal dilation. All right. If you're not sure, if you don't remember all of the keyboard shortcuts, you can go here and you can go here to a list of functions. And there's the sine, cosine, tangent, and all these other ones. Interesting too. That's where they are. And then square root and cube root are going to be at the bottom. Square root is here. And if you want to type a cube root, you could do this and type a 3 where the n is. So go ahead and play around with it for a little bit longer. Whenever you're finished, save your homework 1.7.2. And I'll see you in class.